and your interest in these topics. I feel a little out of place. I have a tie, but I'm so excited to be here in person in a conference to talk to you. It's been a number of years. Yeah, my title is actually very general and overbroad, and I realize now I don't have a lot of time to actually outline what my group does. We're the chemical engineering laboratory that focuses on nanotechnology here at MIT. Here's my group, and I thought I would just give you a snapshot of some of the things that we've worked on before going into my topic today, which is a new lightweight polymer that we can use for infrastructure purposes. So, my group, we're very interested in nanomaterials that then can scale to the macro dimensions. We invented in recent years. We invented a new kind of neoprene. It's actually the warmest garment. Sponsored by the Navy, we've solved a problem for the Navy SEALs where you can use a wetsuit at Arctic temperature water, and so this was a material science problem that we brought into the real world, and competitive surfers have now used it. This is a technology that I'll just point you towards. My group invented this energy generation technology called a thermal resonator. It actually generates electrical power from temperature fluctuations, which are ubiquitous. They're all over the environment. We have a Building 66 on campus. We had a device that we tested for a number of years. You can generate electrical power just from sitting out into the in the environment. And I have a program that looks at turning plants into devices that can replace the things we stamp out of electrical circuits and plastics. And the BBC just yesterday has a video interview that they've done on some of our light emitting plants and other plants as sensors. So please go and take a look at that. But what I'm going to talk about today is an invention that we just published in February, and it's a paradigm shift for polymer science. Almost everything around you now, from the fibers in the carpet, your clothing, your laptop shell casing, it's all made of polymers. And those polymers are one-dimensional in that they're concatenations of these small molecules called monomers into a chain. Okay, so if you look at the nanometer scale and atomic scale, it's pressed spaghetti. Actually, a previous talk gave us a little bit of an insight into that. It turns out that scientists have talked about whether they've asked whether you can make a two-dimensional polymer. That is, a polymer that actually extends as a sheet-type molecule. And it turns out that if you can do that, there's theoretical modeling that shows that this will unlock the ability to have extremely lightweight materials that are stronger than steel, that have really exceptional mechanical properties. The problem is that these materials were thought to be impossible to make. And in fact, many organic chemistry colleagues from ourselves and collaborators said, this is an interesting idea. This theoretical material is called graphamide, and by organic chemistry, it's impossible to make. And so that's what I'm going to focus on today, because we've made substantial progress and we've solved this problem. And we think it opens up the material science space to a completely new set of polymers. Okay, so we're not the ones to call this a dream. This is actually from a review. The idea behind a two-dimensional polymer is to combine the mechanical strength, things like in-plane energy conduction. Some of you are going to be familiar with graphene. But can we make materials like graphene the same way we make polymers at the millions of tons scale per year? So we want these low densities, synthetic processability, and the ability to do organic chemistry. We want to plug these exceptional materials into the infrastructure we have for polymer science to bring them into the real world. And progress on this has been very, very limited. I'll just highlight one. There's research where you can use the silver 111 surface, just a little crystal of silver. You can get this little polymer to be made, but you can't peel it off or do anything with it. So what we looked at was, how do you bulk polymerize? How do you polymerize in 2 dimensions. And this is a quote from a review: making 2-dimensional polymers in homogeneous solution is a dream. There's lots of problems. So what we have done is we have developed the first theory that, that's been validated that opens up the possibility for making these very new materials, polymers that extend in 2 dimensions and are essentially sheet-like molecules. And then our first experimental success we published in Nature in February. And it's a 2D, it's called a polyaramid. It basically is the cousin of Kevlar. Okay, and so it's a 2-dimensional version of Kevlar that all scientific measurements today say it dramatically outperforms Kevlar. Okay, so and it has. So I'll briefly go through what the secret sauce is, and highlight how this opens up the door to other 2-dimensional polymers. There may be polymers that we use in our everyday lives. We can put them in this 2-dimensional format. Okay, so I'm going to give you the crash course in our theory of 2D bulk polymerization. So first, why is it hard to polymerize in 2D? As far as I know, we're the research group that has really codified this mathematically at different scales. Basically, if you try to grow and polymerize in a disk, so each of these disks is a little monomer to different molecules. Okay. What happens is the system is unstable to out-of-plane rotation. As soon as a monomer rotates out of plane, you're growing in 3 dimensions. And that's a problem because it's just basic geometry to show that you will always grow. There's more sites on a sphere than there are on a disk. And so it's a very depressing result. It means for any chemistry, you'll always grow in this 3-dimensional amorphous blob. Faster, much faster than you will a disk. So this is essentially game over. There is, I'll spare you a lot of the math and our theory. It turns out that we discovered a mechanism by which you can get around this. And we call it autocatalytic templating. Basically, a little growing seed of a 2D material that does form before it grows out of plane can template a monomer. Okay, so a monomer can sit on the growing seed and be held in place so that it can then polymerize in 2D. And in that way, materials can actually help each other grow. So it's autocatalytic, means the material itself is a catalyst. It helps itself to grow, and it's auto, so it's autocatalytic templating. And you can show you only need a little bit of this to happen, and you can grow polymers in this way. So it's a completely new game changer. And I'll show you here, these are parameters related to the polymerization. This is the extent to which you can get that templating to occur. And this is the polymer initiation rate. And you're supposed to see that there's an island here, a sweet spot, a Goldilocks spot, where if you can get into the synthetic range, you can make these 2-dimensional polymers. So there are actually two mechanisms. One is you can try to use chemistries that will keep the bond planar, but we don't have complete control over the periodic table and organic chemistry. We have to inherit that. But this autocatalytic templating comes right from nanotechnology. And it's a potentially very general mechanistic pathway that can grow materials in this 2-dimensional configuration. Okay, so let's talk about our first experimental success with this is this cousin of 2D Kevlar. It's a fascinating material. It's amazing. These monomers, this is an acid chloride. This is a molecule called melamine. These are exceptionally cheap. We do not have to synthesize them. You can buy them in bulk quantities. If you polymerize this, you get this polymer. It forms these platelet-like stacks. And this is my colleague in chemical engineering, Heather Kulick, helped us to elucidate the structure. You get these, just like Kevlar, the material likes to hydrogen bond to itself. And so one of the first things we realize is that the material forms exceptionally strong, self-organized films. And the reason why it does that is because it has these chemical groups that like to hydrogen bond. They like to stick to each other like Velcro. Because this is a polymerization, many nanomaterials, you make them and you study them at a very small scale, And then there's a whole research effort. It could take even a decade to scale that up to get a larger sample and see if the properties can scale. One of the attractive natures of 2D polymerization is we've skipped all of that. You actually can make gram scale and kilogram scale right at the laboratory. And so that's the advantage. That was the attraction of 2D polymerization. So you run the reaction. It's actually relatively simple. You make a gel. You can work up the gel. You get this orange powder, and the material itself can then be redispersed in a solvent, and you can use it as a coating and various materials. This is supposed to show you. There are characterization methods that we use for these materials that we've had to invent in order to understand what it is that we've made. So if you're asking the question, why haven't these materials been discovered previously? One is they were thought to be impossible. Two is conventional polymer science tools can only partially elucidate what you've made. So you have to use a lot of the nanotechnology tools. So we use AFM, and I'll show you this on the next slide. The gold standard in the field is to show basically a single atomic layer thickness, which you can see here. This is by AFM. If you spread this on a surface, you get little molecules that are atomic level thickness. This is a technical talk, but I'll just go through some of this. If you take the material, you redisperse it in a solvent. The very first time we tried to spin coat it as a film, we made a beautiful film, and you can control the thickness. And you can see that the surface itself has these steps. So these platelet-like molecules organize. They just spontaneously self-organize and align, and it's through that hydrogen bonding. You can use X-ray scattering of different kinds. You can use polarized fluorescence. On the bulk material, you can show that these platelets like to stick and align inside the thickness. And normally with a nanomaterial, it can take quite a bit of time to then scale this up. Can I make a material that's big enough to actually hold in your hand and you can study? But because we're polymerizing, we have that right here in this paper. So first, interestingly enough, we found that even at nanometer scale thickness, these materials are essentially impermeable. So you can actually do what's called the bulge test. This is an AFM. If you take the material and you put it over a little microcavity, they're completely impermeable to air as best we can measure. And so that actually means they're actually better than any polymer at keeping air out. And that's a signature of this two-dimensional ordering. So we think there's going to be very useful applications as a barrier material, a protective coating that molecules just can't go through, even hydrogen. And the mechanical properties were very impressive. They're in line with theoretical predictions. We've made dog bone type samples. We've been able to roll. My group knows how to make these scroll fibers. So we can make these fibers and do fiber testing, and those are all of those turn out to be quite impressive and support this notion that we've unlocked a new material science space. So I've tried to put some conclusions here. It's not just that we've made Kevlar's cousin. We think that we've unlocked a new class of materials, polymerized not as chains, but as these molecular sheets. Our first invention, we call it 2D PA1, two-dimensional polyaramid 1. It's the cousin of Kevlar, opens the pathway to producing at scale, like train cars, and the properties generally conform to prior predictions. They're exceptionally lightweight. They have great mechanical properties. If you come back in a year, I might have more ideas and maybe applications on build.nano type of things, composite I-beams, coatings, membranes, fibers, panels. But I wanted to link to sustainability, a passion of mine. We ultimately want to utilize less polymer for higher gain. So that's part of it. And with that, I will end and to take any questions that you might have. I want to thank my research group and also thank funding from Army Research Labs and the collaborators that are listed here.
We do have one question for you. The MIT News article mentioned impermeability to water and gases. Can you address that a bit more?
Yes, we were surprised by that, because if you go into the unit cell, at first we were disappointed. Oh, we're not showing this. If you look at that unit cell, it has a large pore. And so when we measured the surface, when we measured the BET surface area, we were puzzled that we got no surface area at all. And so those pores were occluded. You can't get gas inside of them. Then when we made membranes, we noticed, we did this bulge test where you make this bubble. That's mainly a mechanical test. We were pressing on it to get mechanical properties. When we went back almost a year later, we found those bubbles did not collapse. They actually kept their air, very unusual for a polymer. Polymers around you, even your sandwich that you put into a plastic bag, air still does get through that. If you think of like a plate of spaghetti, it has these little volume crevices where gas can go inside. So this two-dimensional stacking appears to lock and keep water and air out. It's this exceptional barrier property of just a simple polymer. It's just one indication that we've unlocked new material properties. And so that's a whole nother application for these exceptional materials. Thanks a lot.
Thank you very much.
Sure.